Let's talk about Fick's law. Fick's law is pretty much a law of diffusion. Uh, for instance, to illustrate it, we have a particle on the left-hand side. On the left-hand side is the initial condition. There are a lot of particle on the left-hand side, no particle on the right. Therefore, we have a density gradient across the barrier, the purple line. As soon as the barrier is taken out, then you would imagine there will be a flux of particle going to the right, just like shown on the right hand side. So to describe such phenomenon, the Fick's law, the first law, describes such phenomenon. J equals negative d gradient n, and gradient of n. J is a flux, d is a diffusion coefficient. So if we can get further this formulary to make it even more powerful in a sense, to couple this equation, the Fick's first law, to the continuity equation. We'll do the following: taking the divergence on both sides, so grad J equals negative d Laplacians. Pretty much this gradient of divergence is a Laplacian, as you show here. We'll plug in the grad J to here, to a continuity equation left with a sigma minus delta dn dt equals negative d Laplacian of n. So tidy it up, we ended up getting Fick's second law. So pretty much this simplified to the point that we have a source sigma and a density as a function of time and space. So we can I will try to attempt to give a general solution of a 1D diffusion. Up to this point is on the textbook. So we have, let's imagine we don't have any source, just a density configuration with an initial condition, and to see how it relaxed to a near equilibrium. Recall from the quantum mechanics, we pretty much separate the variable for a partial differential equation. We just say it may be a function of a t, n equals t dot s. One is time, another is space. This is a common practice, but it's not rigorous. We can just hope that can solve this differential equation, and it does, thankfully. So we plug this possible form of function into the n, and ended up with this equation, and divided by st on both sides, left with pretty much a function of big T and a function of big S. We assume this left-hand side first term equals -1 over tau. Then the second term will be equals to -1 over tau as well. So we solve for, then we separate, we'll make this differential equation to a separate one partial differential equation to two ordinary differential equation, and solve those equations separately. Then I ended up have the solution of those two different functions. Since n equals t dot s, we're left with a general solution in that manner. Of course, as we recall from quantum mechanics, the tau is arbitrary. Therefore, you can choose any tau, and this is it should be obvious by by now in your physics career, it could be a superposition of a few term of that. So let's just study a case with a boundary condition to see what will happen. At time equals 0, we have n equals n naught. Therefore, this term will go to 1. So we're left with only a spatially dependent function, and we can recall from the quantum mechanics we can get the free parameter like a and b using the integration, basically complete the bracket. See, there's a sign, there's a like left bracket, and then the right bracket, you can just do the integration. You can track back to the quantum mechanics, some basic quantum mechanics. So anyway, the essential is pretty much to do the integral of n multiply by say cosine this thing on both sides, and do the integral from 0 to L. Since this is will be a odd function, this over long period it will be 0, average to 0. This will be average to L over 2, and this is what we have. Then we can use the same principle to calculate AI and BI. And then see, we use a real life scenario, say n naught equals alpha x plus b. And then we since this function, if we only look at alpha x, b, we can just add a number at the very end. Since alpha x is odd function, then AI is 0. Since pretty much this solution have odd term and even term, cosine, and odd term, sine. So we can do the integration. Ended up finding. This is I just put into mathematics, I get this, and then you ended up getting B. After tidy it up a little bit, ended up getting BI with this from L over 2 to negative L over 2. And then you pretty much have tau from 0 to infinity, and then you integrate that, and that's a solution of a density propagating through time. Propagating through time and space. The bottom plot is a Python script I wrote that you can use for I basically plot out the diffusion. At first it's like steep gradient, and then slowly the gradient getting lower and lower, eventually get into the equilibrium. So I still have reservation of my calculation. So take this as something definite, but anything beyond that, it will be my hand wavy way to solve the question in general way. Anyway, that's a Fick's law, and then next I will talk about the steady state solution in a separate video.